Hey everyone, so this video is going to be focusing on section 7.8, which is going to be diving more into delta H, change in enthalpy. So we've already seen what delta H is, right? It's essentially just quantifying the amount of heat that a reaction either absorbs or releases at constant pressure, right? We saw that. Realize though that the change in enthalpy for reaction is always associated with just one particular reaction, right? So imagine I'm running a reaction and I get a delta H for that reaction, right? We're not really talking about how the reaction is changing in any way. Like, are we doubling the stoichiometric coefficients in the reaction, right? Like, remember how there was a time we took an equation and we would multiply it by 2 to make the fractional coefficient a whole number, right? Like, well, what would happen to the delta H of that reaction if we multiply in a chemical equation by 2, right? So basically what we're getting at is if we change the reaction in some well-defined way, the delta H of the reaction also has to change in a well-defined way. And we're going to turn our attention to 3 ways that delta H can change when we're changing the chemical equation, right? So 3 quantitative relationships between a chemical equation and the delta H. And here are the 3. Now, I could read them to you, but we're just going to walk through each 3 of these individually, right? But I'm summarizing the 3 over here, and let's talk about each one. So the first one is if a chemical equation is multiplied by some factor, then delta H is also multiplied by the same factor. That's kind of like what I just mentioned, where if you multiply an entire chemical equation by like 2 or something, what happens to the delta H? Well, the delta H is also multiplied by 2. Right? The reason why we're allowed to do that is, remember, delta H is an extensive property. So it depends on, an extensive property just means it depends on the quantity of the reactants that are undergoing the reaction. And also recall that delta H is reported for a reaction involving stoichiometric amounts of those reactants. So if you had an example of a reaction, A plus 2B makes C, and you get a delta H for that reaction. Well, what if we multiply that equation by a factor, right? Let's say we multiply this entire thing by 2 now. So now the stoichiometric coefficients change, right? Now you got 2A plus 4B makes 2C. Well, if I multiply that equation by 2, I have to, according to this relationship that if you multiply by some factor, delta H reaction also has to be multiplied by that factor. If we're going to multiply by 2, we have to multiply the delta H by 2. So delta H2 now, for this new reaction that we multiply by 2, is equal to 2 times delta H1. Okay? Realize I should have also made the 4 and the 2 red. I made the 2 red. Those should be red because we're multiplying 2 over for everything. But the delta H is also going to be times 2. Okay? The second thing is if a chemical equation is reversed, the delta H of the reaction changes sign. Right? This makes sense because remember we said delta H is a state function, which means its value doesn't depend, it only depends on the initial and final states of the system, not how we got to the final state. So delta H is defined as H final minus H initial, right? Now, if we reverse it, the final state becomes the initial state, right? So realize that if we're going to reverse that, we have to change the sign of delta H. So for example, if I have that same reaction, A plus 2B makes C. Delta H of the reaction is delta H1, right? But if I reverse this process, now C becomes a reactant. Check this out. We flip this equation. Now C is a reactant and A and 2B are products. Right? Before there were reactants, and now they're products. C was a product, now it's a reactant. We flip this over. If we flip this equation, we have to flip the sign of delta H. So now delta H1 used to be positive, now it's negative. So your new delta H is the negative of delta H1. Okay. The third one, the last one, is if a chemical equation can be expressed as the sum of a series of steps, then delta H of the reaction for the overall equation is the sum of the heats of reaction of each step, for each step. Let's elaborate on what all that means. So this relationship is called Hess's law. And remember we said delta H is a state function, right? So it only depends on the initial and final states, not on the pathway, right? Not on the pathway. So if that's the case, you could just add up all the individual steps that lead to the overall reaction. And if we had an example of this, imagine we have our A plus 2B makes C, that's delta H1. But now we have C goes to 2D, and that's a separate delta H for that reaction. Now basically what the third point is saying is if we add these up, let me go back to my pen now. Oops, that's not what I meant to do. If I add these up, what do I get? So I'm basically adding these two equations, these two chemical equations. Now, realize that C is a product of one reaction. It's a reactant in the next one. What this really means is that when we make C from the first step, all of C was used to make 2D. So when we add these up, the product C no longer exists because it was all used up in the next step. Right? Imagine, I didn't write this out, and I'm trying to find my eraser. There we go. Imagine this is step 1, and this is step 2. And we're adding the individual steps to get the overall process. So we're taking step 1 plus step 2 to get the overall process. Realize that in step 1, C is a product. In step 2, the product from step 1 was all used to make 2D. So we don't have C left over anymore. There's nothing there. There's no more C. So we have to cross it out. And you'll notice a pattern that whenever you see something in the product side that then ends up being a reactant in the next step, you can cancel them out because the product from the first step is being used in a later step to make something else. And now that you cross these out, you get the overall process. When you add these up, we didn't cross out A, we didn't cross out 2B, that was still there. And we draw an arrow to show that you realize that right now, these are all the reactants. There's no more reactants when you add up step 1 and step 2. The only product that is there is 2D. So when you add all of these up, this is the overall process. A plus 2B makes 2D. And your new delta H, we can call it delta H of your reaction, is equal to delta H1 plus delta H2. Okay? This process is called Hess's law. Everything we just did where we added the reactions, the sum of every individual step is equal to the delta H, of the reaction, the sum of the heats of the reaction for each step. And if you look at this diagram over here, basically what's happening is you're taking A plus 2B, and you notice there's a delta H1 to make C. But then C was used to make 2D for delta H2. And now you have a difference in energy now, right? When you add up delta H1 and delta H2, you get this difference right over here, right, in enthalpy. Right, enthalpy is a form of energy, right? You basically, if you imagine this as a graph, this is your y-axis and this is your x-axis. Your x-axis doesn't really mean anything. It's really your y-axis. You're going up in energy as you go up on your y-axis. Notice in this case, to make C, it took some energy. But then going from C to 2D was a release in energy that's lower than what we started with. So the difference is just this purple arrow here. Okay. All right, let's practice a problem involving Hess's law. So it says the following reaction between solid carbon and gaseous water is an industrially important method of generating hydrogen gas. So we got this reaction, right? And the question is, what is the delta H of the reaction? It says find delta H of the reaction for the reaction using these. Wow, that sounds like way too many reaction words. Find delta H for the reaction using these reactions with known delta H's. And notice we have all of these steps here, right? So this is step 1, this is step 2, and this is step 3. Okay? Now, we're looking at all of these, and the goal right now is to match all of the steps to the overall equation, right? This is the overall equation. So basically what I'm trying to say is all of these, when you sum them up, hold on a second. When you sum these up, they have to equal the overall equation. Okay? But right now, if I add all of these up, it's not going to equal the overall equation. We basically have to manipulate each of the steps. We have to manipulate all the chemical equations from each step to make sure that it can match the overall equation. Now, how do we do that? Let's kind of walk through this. So notice the first one. Let's just focus on the first step. This is the first step. Notice in the first step, they have carbon solid as a reactant. And notice that in your overall equation, you have carbon solid as a reactant. So there's really no need to change this equation. We can keep this one the way that it is. We don't have to manipulate it at all. No change. I'm just going to write no change. Okay, let's look at the second one now. Notice in the second one, in this step, this is a reactant. But in the overall equation, this is a product, right? CO is a product. And not only that, but in the overall equation, we have one of these, right? There's an imaginary one there. But in here, we have two of them. So when we add this up, we can't end up with 2. We have to end up with 1. So what do we need to do to this equation so that when we manipulate it and then eventually add it to make the overall equation, we not only end up with CO on the product side, but we also only have a 1 instead of a 2 there. So what do we need to do? Well, to get something to go from a reactant to a product, we need to flip the equation. So let's do that. I'm just going to write out the first one, that we didn't change the first one. This is step 1. The second one we have to flip over. So we're going to flip it. So now that the CO2 is a reactant, And now the CO is a product. And remember what we do to delta H when we flip something. We have to reverse the sign. So now delta H, it used to be negative 566. But now that we flipped it, we have to change the sign, and it's got to be positive 566. Let me put a positive there. But not only that, we have to change the 2 to a 1. Remember, there's a 1 here. And there's a 2 here. So we flipped it, but we also have to multiply the entire equation. Oops, what happened there? We have to multiply the entire equation by 1/2. Why 1/2? Because half times 2 is going to be 1. And remember that if we multiply an equation by a factor, we have to multiply delta H by that factor. So we also need to multiply this by 1/2. Okay, so what does that become now? Let me go back to red. So now that's going to be CO2 makes CO plus half of O2. And now the new delta H for this is going to be half of 566, which is just going to be 283. Okay? So now I'm going to cross this out because I don't need this anymore because I basically wrote the new one there. Already changed that up. All right, we're done with the second one. What do we need to do to the last one? This is step 3. Do we need to do anything to this? So let's take a look. Notice the H2 is on the reactant side here, but it's on the product side here. Okay, so we already know we need to flip it because if we want H2 to be in the products, we got to flip step 3 so that H2 is in the products. Not only that, but there's also an imaginary 1 there. And we got 2 of these. So we have to do the same thing where we have to flip it and multiply the equation by half. And if we're going to do that to the equation, we have to do the same thing to delta H where we have to reverse the sign and multiply by half. So let's do that. I'm just going to write out the flipped version over here. So we got 2H2O makes 2H2 gas plus O2 gas. Delta H for this, we need to flip it. So now it becomes positive. It was negative, but now it's becoming positive because we flipped the equation. We have to flip the sign of delta H. And now we need to multiply this entire thing by half, which means we need to multiply delta H by half. Okay, so now, what does this become? This becomes H2O gas makes H2 gas plus half of O2. Now delta H here is going to be half of 43.6, which is going to be positive 241.8 kilojoules. All right, so we can cross this out because we've already manipulated this. So there you are. There's our new 3 reactions right over here. This is step 1. This is step 2, manipulated. And this is step 3, manipulated. Notice we kept step 1 the same. We never needed to change that. Okay? Now remember what we got to do. We got to add these up. But before we add it up, let's see which things get crossed out. Which of these products or reactants get crossed out. Well, take a look. CO2 is in the products, right? And CO2 is in the reactants. So these cross out. What else crosses out? Well, notice we got one O2 on the left side And we got half of an O2 on the right, but another half of an O2 on the right of the third step. A half plus a half, if we add those up, is just 1, right? So now we have 1 oxygen on the product side and 1 oxygen on the reactant side. Those cancel as well. Guys, remember, anything in the products, if you see that in the reactants of any other step, you can cancel them out. Okay, what are we left with? I don't think there's anything else that we can cancel. Notice what we have now. We have solid carbon, we have CO gas left on the products, and we have, actually we also have H2O left, and we have H2. So let's add this up, because remember what the whole point of this was, right? We were going to manipulate everything and add everything up. So when we add this up, what do we get? Just going to erase all this. We get carbon solid plus H2O gas makes CO gas and H2 gas. Right? Notice that the CO and the H2 are in the product side. Carbon and H2 are still on the reactant side. And does this match the overall equation? Looks like it does. So we've done everything right. Now we need to take our new delta H's and add those up. If we added all the reactions up and we got the overall reaction, let's add these up. So delta H, let's just call this 1, 2, 3. This is our 1, 2, 3. So delta H1 plus delta H2 plus delta H3 equals delta H of the reaction. Delta H1 is 393.5 kilojoules plus delta H2, which is 283.0 kilojoules, plus delta H3 is 241.8 kilojoules. All right, when we add these up, this is going to equal plus 131.3 kilojoules. All right, I don't know why I did that. This is equal to delta H. I don't know why it's doing that. Delta H of the reaction. All right. I know that was a lot, but let's just recap on what we did in this problem. So the first thing we did was we looked at our overall equation, and we needed to find delta H. And we needed to find delta H of the reaction from a list of steps that have their own chemical equations, and they each have their own delta H. We needed to manipulate each step so that when you add all of the steps, they lead to the overall equation. And how did we manipulate each step? Well, we had to flip it, we had to multiply it, in this case by half, which is the factor necessary to get everything to the correct amounts based on the overall equation. And whatever we did to the equation, any way we manipulated it, whether we flipped it or multiplied it by a factor, we had to change the delta H accordingly based on how we manipulated the equation. And once we manipulated the equation and the delta H's, we then added up all the steps to make sure that all the leftover reactants and all the leftover products that didn't get canceled out, they all added up and ended up looking like the overall equation, which in this case we were successful in doing so. And then taking all of the delta H's after they've been manipulated adding them all up, and finally getting our delta H of our reaction. Okay? These are kind of long, a little bit tedious, but they're really not that bad. And I think it just takes a little bit of practice, right? You saw me do one. I could try doing another one, so why don't I try doing another one with you? So it says, find delta H reaction for this reaction, and use these reactions with known delta H's to help accomplish that. So, let's take a look at all of this. So these are all our steps. So step 1, step 2, and step 3. All right, what do we need to do to each step so that when we add this up, it equals the overall reaction? Well, what do we need to do to the first step? Looks like we need to flip it, right? Because C3H8 over here is a reactant, but in our overall equation, it's a product. So we definitely need to flip this. We don't need to multiply it by a factor because, you know, the product in the overall equation just has one C3H8, and this step also just has one. So we don't need any more. So all we need to do is flip this. So we're going to flip the first one. And if we flip it, we have to change the sign. So now it's going to be 2043 kilojoules. All right, so why don't we flip that? Why don't we write up the flip version? So new step 1. New step 1. So the new step 1 is going to be now 3 CO2 gas plus 4 H2O gas makes C3H8 gas plus 5 O2 gas. Delta H is going to be positive 2043 kilojoules. Okay. What do we need to do to the second step? Do we need to do anything? Well, notice that the carbon solid is a reactant in step 2, and it's also a reactant in our overall equation. So we don't need to flip it, but notice there's 3 of them in the overall equation, but there's only 1 in our step 2. So if we're going to need 3 of these, what do we need to do? We need to multiply that equation by a factor of 3. Right, so we're going to multiply this by 3, which means we have to also multiply the delta H by 3. Okay, so now we have our new step 2. New step 2. That's going to be 3 carbon solids plus 3 O2 makes 3 CO2. All right, we multiplied everything by 3. The delta H for this is now going to be negative 393.5 times 3, which is going to be negative 1181. You could do that on your calculator, but that's what you get when you do this math. This is negative 1181. Okay, do we need to do anything to step 3? Well, let's take a look. H2 gas is a reactant here. It's a reactant in our overall equation, so no need to flip the equation there, but there's 4 of them, and we only have 2. So what do we need to do? We need to multiply by 2. Which means you need to multiply this by 2. So our new step 3 is going to be 4 H2 plus 4 oxygens makes 4 waters, 4 H2Os. And the delta H for that, what is this equal to? This is negative 961 Whoa. What the heck just happened there? All right, I don't know what happened. Give me a sec. Okay, there we go. Oh, that makes me nervous every time something happens with the screen. What was this? 967.2 kilojoules. 967.2 kilojoules. Okay, so now what do we need to do? Well, we've manipulated all our equations. Let's add all these up. So, question is, what crosses out? So notice that the CO2 cancels out. Does the H2O cancel out? Yeah, check that out. That cancels too. What about the oxygens? Two. I feel like we did something. Oh, why did I get 4 over here? You guys have probably noticed I made a mistake. All right, for whatever reason, it's not erasing, but this is supposed to be 2. Right, because there was only 1 here originally. We multiplied it by 2. I don't know why I put 4 there. So for those of you that caught that mistake a lot earlier than me, sorry about that, but it's fixed now. Notice we have 3 oxygens in step 2 and 2 oxygens in step 3. That adds up to 5. We have 5 oxygens from step 1 in our products, so those cancel. Those all cancel. All right, what are we left with? We're left with this, this, and this. Let's add them up. So now what do we get? We get 3 carbon solids plus 4 H2s, right? Notice that's all on the reactant side. And the only thing we have on the product side that's left over is C3H8. And voila, this matches our overall reaction. So we're good to go there. The only other thing we need to do is calculate delta H of the reaction, which is just adding up all of these. So add all these up, add all of them up. And when you add all these up, you should get negative 105 kilojoules. Okay? So, hopefully you guys understand how to use Hess's law to find the delta H of the reaction. Right? Realize the individual steps and their delta H's have to be given to you. And all you're doing is manipulating those steps so that when you add them up, it matches the overall equation, which is given over here, right? This is the overall equation. And once you know it matches, you've done everything correctly as far as manipulating your delta H's in correspondence to manipulating the individual steps. And then once you have everything looking pretty good, you just add up all the delta H's, take the sum of them, and you get your delta H of your reaction. Okay? So I have more practice, so why don't you try this one on your own? This is going to be on a problem set. Definitely, like I said, take your time with these. Don't rush these. One of the things students like to do with these problems is they like to just rush, flip the sign, multiply by a factor, and they start losing track. You need to be meticulous with this process because you need to make sure that everything cancels the way that it's supposed to. When you add all of the steps, it should match the overall reaction. Only until you know that when you add the steps and it matches the overall reaction can you be content with being able to add up all the delta H's that you have. Okay, so be careful with this. Here's another practice problem as well. So I'm leaving 2 practice problems for you to do. I'll post the answer keys to them so that you could check. Make sure you get those done, and you guys will end up understanding this, okay? All right, thanks. One more video for Objective 12, and that should be it, so stay tuned for that.